Guys, we'll be doing one more video of the same Java applet that we used earlier, but this time we'll be making sure that we're talking about two or more forces on, let's say more than two forces on the seesaw. So we'll see how we'll use our law of moments. We'll make sure that physics is working. So this is where we got the Java applet from. It's PISJ-ES.colorado.edu. So let's see. I have the same seesaw here, right? And I am placing a mass of 20 kilograms here. Now obviously it's producing a turning effect because this is the only force that is acting on this point. This gives it a turning effect. Now let's see if I need to balance this. Let's see how I'm going to balance it. Let's say I put a 15 kilograms mass here. Still not balanced. This one is still heavier. However, if I use this one somewhere here, I might be able to balance. If I use this 5 kilograms mass somewhere here, I might be able to balance this. Let's see if I am able to balance this. So first of all, this is our example, and let's see first mass, which I am saying mass 1 is 20 kilograms. So always remember that this is not the force, this is simply the mass. So let's find out the force associated with this mass, and we know this is simply given by mass times gravitational acceleration. So force is equals to 20 times 10, which gives me 200 newtons meter. And since this moves it in this direction, this mass moves it in this direction, so this is 200 newtons meter in the clockwise direction. Now remember that in such cases we always use the law of moments, and we have been using this earlier, which says sum of moments in the clockwise direction should be equal to sum of moments in the anti-clockwise direction for equilibrium. So what am I doing essentially? I am simply looking at the forces that would produce a clockwise moment, and I can see that this is the only force, since it's on the right side of the pivot. This would produce a force in this direction because the force is downwards, and it would take it in clockwise direction. There's only one force. What I can say, this is how I would numerically solve it. I would say this force, which I say force 1 times distance of this force from the pivot, would be equal, for equilibrium, should be equal to some second force, which would be given by this mass, because we know that this would take it to the clockwise direction. So the force given by this mass, let's say it would be F2. I don't know what the forces are. I would calculate this one. So F2 times the distance 2 plus, because it's the sum of the moment. This is moment of this will give us the moment associated with this mass only. But we are planning to bring in this mass also to balance the situation. So there will be one more force. So I will have to add that the moment associated with that force to our equation if we need to balance this. So that would simply become the force associated with that mass would be F3 times its distance from the pivot, which would be D3. So let's see. This force was 200. This is simply newtons. This was 200 newtons times the distance 1. The distance of this from the pivot, which is 1. This gives me 1, is equals to this force times distance. This is 15. This is the mass is 15. So the mass 2 is 15 kilograms. So the force associated with this mass, let's just would be m times g, 15 times 10. This would be 150 newtons. So this would be 150, the force associated with this mass in the anti-clockwise direction. This would produce a moment in the anti-clockwise direction, times distance, which is 1.25 meters. Plus, this is one bracket here, plus for the third force, which would be because of this 5 kilograms that I would put somewhere here. And you can see that this is not balancing here because we are not putting at the right distance. So we have to find this distance. So this force is, the mass is 5, and you know by your experience that force is simply mass times gravitational acceleration, which we take 10 for simplicity. This becomes 50 newtons. So 50 newtons times the distance, the d3 that is unknown. We don't know this distance. So let's take it as d3. We have to find this d3. So this is 200 is equals to 150 times 1.25 would give you simply, if you just find this out, you would get let me see, this is 5 times 5 over 4, and this would give you 150 and let's see, this would be 37.5. This is 187.5 plus 50. You can use your calculators here and see that if this is the exact value. I don't have a calculator right now, but let me just check if this is the correct value. Yes, it is 187.5 plus 50 d3. So remember this equation, we'd be, and let me just clear this and we'd continue. So the equation was 200 is equals to 187.5 plus 50 times d3. So let's just switch it here, and since this is a plus, it will go here and become a minus. 187.5 is equals to 50 d3. 200 minus 187.5 would give me a 12.5. So 12.5 is equals to 50 d3. Now d3, divide both sides by 50 simply. So d3 would be 12.5 divided by 50, and if you use your calculators here, you would get 0.25 meters, which says that if you put this 5 kilogram mass at a distance of 0.25 meters and this 15 kilograms mass at a distance of 1.25 meters, it would produce an equal anti-clockwise moment, similar or equal to the moment produced by the 20 kilogram mass at a distance of 1 meters. So let's find this out and let's see whether physics is actually working or not. So this is at 1.25, and let's just put this at 0.25, and you can see the lights are blinking, which means that this is balanced. 20 kilograms at 1, 15 kilograms at 1.25, and 5 kilograms at 0.25. So you can see that this is actually working, and we have balanced the situation. However, let's say this is simply the balanced situation. What if I just take this here and put it right here? And my question to you now is, find out the net moment of this situation. So the net moment is given by the sum of clockwise moment minus, or let's say add the two up, anti-clockwise moment. I'll tell you how you do it. It's simply, the net moment is simply given by the addition of two moments. However, because we know that the direction of two moments, of both of these moments, are opposite to each other, and moment is a vector quantity, the direction is of importance, so we will have to assign a positive sign to any one of them and a negative sign to the other one, the other that is left. So let's just randomly give the anti-clockwise moment a positive sign and the clockwise moment a negative sign. So whenever you would be computing an anti-clockwise moment, you would use a positive sign, and for a clockwise moment you would use a negative sign. That is totally arbitrary. It's not set. You can decide it for yourself. I mean, it can depend on the situation. It's your choice completely, but it should be consistent throughout your operations. So let's find out the anti-clockwise moments first. Which is because of these two forces. One is here and one is here. So the first force is 15. This mass is 15. The force would be 150 newtons. Simply, this is the weight, mass times g. And the moment associated with this force is 150 times its distance, which is 1.25. So this would again give me 187.5 newtons with a positive sign, because I've stated above the anti-clockwise motion will always be positive. Now the second anti-clockwise moment is given by the 20 kilogram mass here at 0.75. So first of all, find out the weight of this 20 kilogram. This would be 20 times 10, which is 200 newtons. And the moment would simply be 200 times its distance. Mass, force times distance. This is the moment. So 200 times its distance, which is given by 0.75. So if you find it out, you would get a 150 probably. So you can just check, and this is 150 newtons. Again with Newton meter, again with a positive sign, because it will produce an anti-clockwise moment. So now that is done. However, there is also a clockwise moment. Remember these values: 150, positive 150 newtons and positive 187.5 newtons. So we'll come to this. Now finding the anti-clockwise moment. Sorry, the clockwise moment. Which is only because of the 20 kilograms mass here. So the force associated with this 20 kilograms is simply 20 mass times g, 20 times 10, which is 200 newtons. The moment associated with this force is 200 times its distance from the pivot, which is 1 meters. This is 200 newtons meter, but with a negative sign, because this is clockwise, and we decided earlier that whenever there is a clockwise moment, it would be given a negative sign. Now we had three values. What were the three values? If you can remember correctly, the first one was positive 187.5 newtons. The second one was positive 150 newton meter, and the third one was this one, minus 200 newtons meter. So the net moment, because it's not an equilibrium, if it's not an equilibrium, there has to be a net moment. The net moment will not be zero. That is the condition for equilibrium. The net moment is zero. But if it's not an equilibrium, if it's not stable, then definitely there is a net moment. So let's find out the net moment. So this would be positive 187.5 plus 150 plus minus 200. We are still adding all of them, but this has its own minus sign. So what can we do? Now let's find out the answer to this. 187.5 plus 150 minus 200. This is 137.5 newtons meter with a positive sign. And this should tell you, because of your own decision, this should tell you that this is a clockwise moment. Sorry, anti-clockwise moment. I'm sorry. Don't get confused. This is an anti-clockwise moment. And you can see from here that there is a net moment which is moving this seesaw in the anti-clockwise direction, because the net moment or the total moment is in the anti-clockwise direction. So we have found out how to calculate when there are more than two objects on the seesaw, how to calculate the positions if we want them to be in an equilibrium, and also what happens if they are not in an equilibrium, when there is a net moment. How do we calculate that? So remember these steps, guys, and I hope you understood this. If you have any queries, kindly just comment in the box below so that I can reply to them. Thanks for watching, guys. Stay tuned.